Welcome back, everyone. First, I want to ask your understanding and ask for sort of forgiveness, because it turned out that I had a goal to cover organic 1 material in handful of video, and as I filming, it turned out that it is much of stress and pressure, because you can't actually cover organic 1 with a decent depth and enough of explanation and in different various methods within just few videos. So very frequently I'm rushing, and that causing mistakes and also like lack of enough of time on certain subjects, and I'm skipping some very fundamental things. So yeah, I'll try my best to make the video as short as possible, but it's not easy. That's my confession. So last few videos we've been talking about organic reactions, and we are continuing on that. So we've been talking about substitution, like Sn2 and Sn1, but we were focusing on Sn2 after I gave you the overall picture. Yeah, we also briefly talked about elimination, bimolecular and unimolecular. Then always the unimolecular reactions competing with the rearrangements to the more stable intermediate, like from primary radical or carbocation to the higher degree more substituted ones, because that way those sp2 carbons with a charge or radical center stabilizes the molecule's electron better. So we're focusing on this, and we said addition reaction is opposite of elimination, although there could be some slight difference. So the Sn2 was when you have carbon chain, say simple carbon chain like this, it's better to have a leaving group on the primary carbon because it has a less steric problem. If you have a leaving group here, then it could cause more trouble, because you have now hydrogens sticking out and blocking the incoming base. So unless you have OH minus or linear small molecules like a CN or things like that, it's pretty difficult to have substitution here. Another way of having reaction there is to have a very good leaving group, and then the base with a big size like sulfur. So the typical example is the one that you have a leaving group here, the leaving group such as a chlorine. Any halogen except the fluorine will be a good one. Then some functional groups with a resonance is considered good leaving group. One of the best is the oxygen with a multiple resonance ability with a sulfur. You can have a methyl group, or even the benzene with an electron withdrawing CF3 with a 3 electronegative fluorine pulling electron. That's called triflate. If you have a CH3, that's called tosylate. So those are on the oxygen, and that oxygen negative will be stabilized by tosyl group or triflate group. So these good leaving groups will have very easy Sn2 reaction with a simple small size and strong base. Even I said neutral nitrogen or sulfur is considered as a decent nucleophile that can attack carbon rather than hydrogen. So this case, I hope you can draw the Lewis structure of it and imagine, you know, those hydrogens sticking out, so you can see the backside attack and have an inversion of configuration. Then you're gonna have cyanide sitting here, but that's gonna be eclipsed, so rotation gives cyanide coming down here. And you have a chloride as a, you know, conjugate base that makes the reaction comes forward. So we talked about this many times. So this arrow drawing scale with all these considerations you need to make is called mechanistic scale, and all the Hammond postulate related you know, potential energy diagram theoretical knowledge also is crucial to tackle any variations. So that's the first thing you have to do. How do you come up with a product based on your mechanism knowledge? So typically the normal carbon chains, if it's a primary, easy. Secondary, then you have to worry about the size of the base, like we said before. However, when you start to have rigid ring structure or having secondary functional groups, then you actually have to be careful. You don't want to just go by primary Sn2, you know, that's too simple-minded. So don't do it. So when you show mechanism, please fully consider all the features of structures and charges with other variations. But even a simple case, the beginners having hard time to deal with a different type of situation. Like I pointed out last time, not the case you have reactant and conditions reagent, but the case where you have to find I had this, then what do you need to make something like this, the benzene with the sulfur? Then you know you have to compare these two. We talked about this, right? So, okay, I lost this, which is a good leaving group. Instead, I got this. So do I want substitution unimolecular or substitution bimolecular? Then there's a couple hints. In order to have a unimolecular, you need to have a lot of conditions. You should have a weak base, but also heat, and you should have a stable conjugate base as a product, but also the carbocation you are making must be stable one, like a tertiary at minimum, secondary. So if you look at this, it's a primary, so it doesn't make a carbocation easily unless you have some sort of a catalyst. We're not going to talk about it yet. So we say, safely speaking, I don't want to try SN1. Let's go for SN2. That means the attacking group that replaces this, which is this one, should be in the strong form. Then it should be preferably small group, but you have no choice though, right? You have to attach it anyway. But you just consider, oh, I have a sulfur, then it's no problem, because the sulfur likes carbon anyway. So then when you put this thing, you can put it in a strong form. It might still work with a weak form, but because you want to do SN2, you come up with a strong form, and this is it. Then, like I said before, in previous video, when you know reactant and condition, typically you draw mechanism and come up with a product, like previous case, and you have that technique. But like I said, there's another type like this one. You have a reactant and product given, then you can guess many conditions, like SN1 condition, SN2 condition. Then which one you choose? I said you have to go back and try. Sn1 condition, let's try, see you get what you want. If it doesn't work out, then Sn2 condition, you try. Then if the product according to your mechanism skill, you come up with certain product. If that matches with that, then you know the Sn2 condition you guessed, out of these two options, that works. So that's how you approach this type of problem. What if you have something like this? And you have compound, something like this. Then, there is a situation like this. You were running some reaction, and you came up with a weird product you never expected. And you used this kind of base for your reaction you planned. Then you need to know what caused this kind of product. That's the realistic situation when you conduct research. So what could be possible reagent that caused this product? Then you have to compare what you have as a reagent and the product. Then you see the reagent is in the product, and that means something fully bound carbon in the reactant lost something, and instead you got that. So you look at the remaining part of the product, which is a CH3. So you can guess, I may have a CH3 as a reactant, and then I had some leaving group, like this. Then you say, I came back to the first type. When you don't know the reactant, but you knew the conditions and product, you have to guess what the reactant would be. So a couple options, like here you have to guess couple conditions, right? So couple options you consider, and you try one at a time. So this time I try this and see it works. This is a pretty simple reaction, so you don't have to guess, you think, but just for the sake of practicing and building up the strategy and practice on making strategy, just pretend this is a complicated molecule and working on it. So if you have the base and electronegative pooling, there's a positive charge, so this could be good acidic carbon, especially because it has a good leaving group as a product, stable conjugate base. And you start to push arrow, and then this is very simple. There's no complication like a ring or other functional group. It's even more simpler than straight chain here. So it's typical Sn2, no steric hindrance. It just attacks and you got it. So this is perfect. So this caused this. So you search for the clue. Where did you have this in the reactant you didn't expect, and then you can eventually solve your big project problem. So as you get, when you study organic reactions, of course you first need to know typical type of reaction. So typically primary simple substrate with a no complication reacting with a simple strong base will give you dominantly Sn2 mechanism. When you come up with a product structure, though, you have to actually draw arrow and imagine flip of the center. So you can predetermine type of reaction, but so many cases you can't do it because it's too dangerous. Your decision based on just the primary target and then strong simple base might cause problem. I want you to again analyze and draw mechanism as you consider all the conditions and come up with a product. Then see that is SN2 style of product, not SN1. Or elimination. Elimination obviously must have a double bond, so not the case. I mean, not just double bond, but additional pi bond formation. But SN2 type, just like no arrangement, right on the carbon where you had a leaving group. SN1 type would be like there is some rearrangement, some movement on the backbone. So predetermined type, then you automatically connect the condition. Okay, so say here like we did here, okay, we can predetermine type and see you come up with a typical condition according to the type like we did here, and you do it. So for that you need to remember typical conditions and typical type of a mechanism. But there will be many reagents, so it's better if you can guess what type of the reaction these bases can actually cause. Then slowly you get more exposed to this type of realistic situation. For that you need to have a more long-term builder's eye kind of training. So you always have to have a ability to choose among the few options which is better by trying your mechanism with your individual choices. And there are cases your theoretical skill matters as well. But let me throw in another situation here for you. Say you had this and you want to make this. Then you analyze, okay, I have a substitution. Will it be SN1 or SN2? You might ask yourself, you have to. Then it might be SN2 because first it's a primary like we said. If it was SN1, you don't even break, but even if you did, the primary carbocation will shift to the secondary. So you wouldn't get the product on this carbon. Chlorine should be on the secondary carbon here as a product. So we know SN1 is not what you want. Then you say, okay, SN2, you need the nucleophile that you have in the product as attacking group, which we did over here, here as well. Then you have to think about your theoretical, have to use your theoretical knowledge. This is the reactant you want to use. If you use it and you aim to attack the primary carbon with a no steric hindrance and kick that out, then you have the product, this, which is not as stable as the reactant. So this is endothermic. So it's not going to work. Then theoretically, if your product is not as stable, you can just stabilize it. Then you will have exothermic reaction. So how can you do that? So there. This wouldn't work, so we have to think about how to lower the stability. lower potential energy to increase the stability of the leaving group. So, in terms of stability, we have to provide more attractive force, or, remove repulsive force. So we can achieve that by adding H+. If you have H+, you can imagine that reacts with H+ and it becomes water, right? Then it's very stable product. So when you have H+ given, this reacts, then you have positive oxygen, very powerful atom pulls electron already toward the oxygen, causing carbon highly positive, make it better acid. So even chloride, stable one, able to attack, push away with the early transition, meaning chlorine is far from the carbon center, yet that repulsion is enough to causing bond break. So you reach the early transition without causing much steric hindrance between these neighboring hydrogens and carbon with the incoming base. So you can make that. Like I explained, there's something you need to remember for now. How do you make oxygen better leaving group? Instead of giving just H+, sometimes H+ causing trouble. When you have other multiple functional groups, you'll have to worry about that later in the organic. So you might want to consider using SOCl2, thionyl chloride. It looks like one of the examples we worked on in the structure. The sp3 hybridized sulfur forming pi bond with the p orbital of oxygen and d orbital of sulfur. That sulfur is partially positive and have a two good leaving group, make the sulfur very Lewis acidic. So the oxygen will eventually attack sulfur and kicks out the chlorine, and then solvent's gonna remove hydrogen from there. That mechanism we'll deal with later, but just remember SOCl2 is the another option for now. So the oxygen losing hydrogen, instead you got the sulfur on it, and then sulfur lost the chlorine, instead sulfur got the oxygen. So this one now has oxygen resonating with the double bond in the transition state or in the product state. So the oxygen OH became much better leaving group with the conjunction with the sulfonate SO double bond. So when chloride attacks, the chloride kicked out by the OH, you can easily kicks out this group and you will get the same product. That's another option. So this is one of the type we had our question before, also similar to this previous example. So typical analysis leads you to the SN2 and you realize that SN2 is not going to work because leaving group is poor. Then you need to remember, okay, I need to make this poor leaving group better. Then you obviously add H+, and you need some nucleophile that stay in the product to replace the poor leaving group. So you need Br- in SN2. But again, you have another way of replacing OH. This time it's phosphorus with a 3Br, tribromo phosphonium. So you need to remember these reagents and their role. So whenever you think of the situation, okay, I need to convert this better, poor leaving group better, then you need to bring these up. Depends on what leaving group you want. Okay, then either you put your leaving group here, or something like this. We dealt with this type of leaving group, right? You can make the carbon here acidic, because you can have a resonance through these 3 atoms, so it can be decent leaving group. And that carbon's a better acidic carbon than this, although it has probably 2 oxygens taking away electron, because the conjugate base you are forming by attacking on this one, by breaking pi bond, is just the oxygen with a low resonance we talked about. So you would not have much reaction occurring here, mostly there. Then that secondary carbon is causing steric hindrance by imagining 2 hydrogens sticking out and the 1 hydrogen or 2 sticking out, and even 1 carbon base in the transition state and staggered conformation, it causes about 30 kilocalorie or even more. So that's a serious. So anything bigger than this, or even this one at the slightly elevated temperature, it's looking for more of elimination. Like we said, when steric hindrance pushing the Lewis base away, it's not anymore nucleophile, it will act as a base, and you have strong base causing bimolecular, and now you are looking for hydrogen partially positive on the beta and beta position. So here and here. Then quickly you say, can we choose? They attack both, but as you increase the size, say like tertiary carbon with a lot of hydrogens causing trouble, and the lone pairs, let me see, tetrahedral arrangement of the lone pair, make the T-butyl group tilted down. It's not like straight and attack the carbon, right? It's not like this. So when this attacks hydrogen, that's not a problem, not much of a steric hindrance, but still this prefers this one exclusively. Smaller ones, primary, couple more carbons, like ethyl propyl or even isopropyl, it's somewhat sterically hindered, but still will prefer here for attack. And there is some stereochemical requirement which I've been ignoring, especially for the ring structures. The open chain, they can rotate and adjust, so we automatically assume it's okay. But time to time you have to find out whether you get the cis isomer or trans isomer or E or Z isomer. Then you have to know which conformation gives what product. So it's always best, consider the stereo chemical consideration in the mechanism. So I'm going to show you that after this. If you attack here with a bigger base, electrons pushed away toward the positive and causing pi bond, that makes the electron here on the second shell of this carbon pushed away to the oxygen going through the transition state. Okay, that transition state has partial double bond. As you break this bond partially, as this oxygen, upside down, you have a T-butyl group. Then you are losing the leaving group. You might have some partial double bond and broken bond, partial 1.5 each bond in transition state to form this product with the leaving group. Either way you get same leaving group, so let me just forget it, and that leaving group is more stable than this one without leaving resonance, therefore the product is more stable. When you attack here, these electrons are not going this way, the carbon cannot accommodate it, and there's no atom that can stabilize the inflowing electron, so obviously you choose to go this way with a positive charge, and then therefore you have some group that accommodate electron better than the reactant base, so it goes that way. That makes second transitional state 1, transition state 2. So there you have hydrogen bond, bond with the hydrogen broken. So the partial charges, negative charges are spreading all over. Then you get the product with double bond there. In this case, I showed you trans. So let me first talk about Zaitsev rule. Sorry, let me change the color. Zaitsev rule addresses the stability of the double bond. These are the regioisomer you can form. The same formula, it's just that where you put your unstable pi electrons. You put the pi electrons here, equally unstable, but because you put the sp2 carbons here and here rather than there and there, you have the more stable electrons. Because sp2 carbon stabilizes these electrons, causing further stabilization of those attached hydrogen and so on. There you have only this group giving significant amount of electron to the sp2, so which case you stabilize the molecule's electron better? Here. So simply speaking, when you have the double bond, the circle, the double bond has more substituted carbon, this case 2, this case 1. That case you have a more electron to stabilize, so here electrons, here electron pools get stabilized, so that's more stable product. So when you show same reactant, two different paths making different stability, and the energy difference is about, roughly speaking, 3 kilocalorie per mole. So 3 kilocalorie is not trivial. When you have an equilibrium between these two going back and forth, and they choose more than over 90%, 3 kilocalorie means more than 90% choice. Even 2 kilocalorie is more than 85% choice. So it's a couple kilocalorie makes big difference. So that one with the transition state 2, let's say product 2, product 1, the product 2 is more stable with the, but2-ene than this. That's major. Also, you can say your transition state 2 is more stable than transition state, sorry about that, transition state 1 with a later transitional state than this. So transition state 1, transition state 2. So you have a much faster reaction with this. So this case I made a mistake. Let me correct. This wasn't T-butyl. This was the smaller one. So isopropyl group or small methyl groups. So you form more stable product with a smaller, more stable one with a smaller base. You can form more unstable product with a bigger base. So people call this as a Zaitsev product and that as a Hoffman product. If you want this one as your choice, you can choose. You just simply increase your base. There are other factors, but that's enough for now. Therefore, the Hoffman product is what you want. You know what the factor you can play with. Then, as you pull this out, the sp3 carbon becomes sp2, losing one pair of the bonded electron, turning into pi bond. And pi bond is made of 2 p orbital. So the p orbital is unmixed. So the carbon becomes sp2, right? We talked about it. Let me show you more clearly with the Newman projection. Now it's time to use our lesson to understand chemistry better. If you see it from there, you have this carbon with the 2 hydrogens in methyl group and this carbon behind, away from your eye, so it's behind this ball. Then say you have methyl group here, then sp3 carbon must have 2 hydrogens like that. Then I want staggered. Since they're not specifying wedge or dash, let me just put one here. If that was wedged, then there is a dotted hydrogen pointing down from this perspective, right? So I can see this methyl group coming here. That's methyl group. Then pointing up, the wedged line is oxygen. Then these groups are not tilting down to get closer to the hydrogen because there's no attraction. So probably you want to do this. Then here you have the hydrogen on the dotted line on this carbon. Then we can say the red hydrogen is one of these two. But I say this one is inactive. Again, that makes sometimes difference in terms of Z isomer or E isomer. Although they are able to freely rotate. It's inactive because when you pull out, these two losing hydrogen will, go towards it, right? We talked about in earlier video. Then this hybridized orbital turn into p orbital, unhybridized orbital. So there will be imaginary p orbital forming through the transitional state. Okay, let me draw it. Take some time. You see what I mean by rushing? I'm rushing. So as you pull this hydrogen away by using the electron of the base, whatever the R group we are assuming, at the moment it should be the smaller one, but then as this one pulled away, because the positive is attracted to the negative electron of the oxygen, they are feeling less repulsion here, more repulsion there, so they go like flat. Not really flat yet, but I'm exaggerating. It's getting there. So you have hydrogen, this hydrogen, and the methyl group. And you can see your p orbital is just slowly forming here. P orbital start to form. This lobe will still grow, become full p orbital later in the product. Then it's supposed to, as you remember, the electron here go to the double bond area. This goes to the double bond area because the oxygen is pulling electron and getting, stable, more stable conjugate base. And for that, electron need to flow here and then push that away. But electron is here, and you want to give electron, but if you look at the arrangement of the orbital behind, there's no orbital lined up on the behind carbon. So this electron cannot move, it stays. That means electron in the p orbital not getting stabilized, so it's unstable, so this transition state is not going to work. Yes, you can move and turn and make it better. But before we turn, let's consider as it is, as we saw from this drawing. Then, if you attack this guy, pull away, and these guys coming this way, and you are making p orbital right here. So let me show you the second transitional state. Now these two becomes nearly flat, and this is far away, pulled away to be transitional state. Then electron going into the p orbital. Then right there, we didn't do too much about orbital, so I'm trying to avoid too much discussion about orbital. Then electron can go. Then you see, as electron go, you can push away this. Then these two are going from sp3 to the sp2 arrangement, the flat arrangement, which is this direction, upwards. And going to be eclipsed and flat. If you see this molecule from this angle, you will have 4 lines on the 2 carbon with a double bond, flat. And as it leaves, you develop another p orbital here and behind. I cannot show because it's behind. Then they can overlap and make a double bond. So this one's active. Therefore you get hydrogen, CH3 flat out, and CH3 this one, and hydrogen flat out. See, from there you have a double bond, right? Double bond here. Therefore, if I see from there, you have double bond with hydrogen here, methyl group here, this hydrogen here, methyl group there, trans. But is this most stable conformation? Well, not really, right? You have gauche here. So they repel. Do they go this way? Then putting methyl group causing gauche interaction, repulsion, it's even worse. So you move this one this way 60 degrees. So let me show you. And if you have methyl group here, hydrogen comes here, here and here, right? Then you can imagine these hydrogens, if you pull away, the p orbital you're forming is not lining up with this p orbital from the leaving group. So this conformation, although it's the most stable, as you see, most stable one, does not work. Okay, let's slow down. Let's show it. So if you move one more click and put the methyl group over here, bring that hydrogen there. Sorry, if you move one more time here, right, that hydrogen comes here and that hydrogen comes here. So let's try that one. More rotation, putting methyl group here, hydrogen there, with the O acetate group, methyl group, hydrogen. Then this hydrogen become active, which was this inactive guy in this conformation. Both have a similar conformation, but which is a better. This one we said has Gaussian, worst. That one has only one Gauss, although this is best inactive conformation. The worst ones, fortunately, active, but you don't have to use it because you have another second most stable conformation having this hydrogen. So if you use this hydrogen, then you get the trans as a product. So is it only way you can consider to see those beta hydrogen and the leaving group to be coplanar? Coplanarity. Not really. You have a couple ways. Let me see. What if you turn this one 60 degree, not 120 degree? Okay, only 60 degree. Then you can make this one and oxygen. Let me use different color for the front lines. So this goes here, right? Eclipsed H. And methyl group comes over here, hydrogen goes there. Then when base attacks on this hydrogen, you remove this and this pair becomes p orbital, and these go to the planar upward, and you have a p orbital forming right there, and that's able to give electron to form double bond because you are able to push out, and that p orbital forming in the back is coplanar to the front one. So that's the case. Then you have two methyl groups on the same side, so your double bond have a methyl group here and hydrogen group there, and your behind carbon lost leaving group, but methyl group here, hydrogen there, and that's a cis. So the cis is coming from this unstable conformation, eclipsed, so this must be minor. It's not only because the product is unstable, it's really because the reactant conformation is unstable, less probable to have a reaction because it doesn't live long enough. So that is the real reason why you have trans in this case. Is a trans always the major? It really depends. That's why you need to analyze the structure carefully before you run the reaction on the paper, before you do reaction. Well, when you deal with a cyclic compound, now you must consider the stereochemical elements. Okay, because you have an axial lining up only with the axial. If this is a leaving group, the beta hydrogen you can attack is only this and this. But what if you don't have these guys? What if you have here other things like methyl groups? Then you cannot have a reaction. Then you can say, well, these are not stable, let's send them to the eclipsed. You have to flip. The flipping make the more stable conformation. You're right, because the axial goes to the equatorial. So those hydrogen must come to the axial. So hooray. But those axial cannot react anymore. That's because the leaving group is not anymore on the axial. They are in the equatorial. So equatorial and the axial, they're not lining up. If you see, they're staggered. Even the equatorial and the equatorial, if that was even hydrogen, it's methyl, but if that was even hydrogen, you cannot, because they are not eclipsed, or they're not anti, they are staggered. So you need to know how to draw Newman projection. So go back if you're not clear to the video where you have to look at the cyclohexane chair form from certain angle and see how you can draw Newman projection. So take my word, none of them will be coplanar to equatorial leaving group. Axial leaving group has a chance, but if they're not the hydrogens you pull off, then you can't. So this makes a lot of complication in real life. So hopefully you can see that comparing Sn2 and E2 is not just about more bulky base or secondary, tertiary, more sterically hindered substrate, but other factors must be considered. We have a long way to go. I don't know how many more videos I can make up to summarize the remaining reactions for organic 1, but for now, let's just say we'll do our best. See you next time.